All right, folks. Welcome to another fun-filled dynamics video. Today we're talking about the conservation of energy, and we are looking at it's called a reverse pendulum. There's a 15-pound ball on top. It starts from here, which they're calling theta equals 0, and it's released and it's going this way. The rod is considered massless. It's 3 feet length here, and they're asking us to find the angle when the compression force in the rod becomes 0. So when F equals 0, this tells me Newton's law, and then when it becomes 0 means that it's traveling. That tells me energy. So let's start with the forces. So we draw 2 circles, right? F equals ma, and what are the forces? Got the weight, it's W, got the force from the rod, and this angle, this theta. Okay. Direction of travel. This is mat. That's a subscript. And this is man. Again, subscript. And the sum of the forces is, let's see, coordinates. Let's just use this. Call this N. Call this T. And we're interested in the force in the rod, right? So when the force acting on the ball is 0, then the force acting on the rod from the ball is 0, and the rod is no longer in compression, right? So if we do a sum of the forces in the n direction, then that's going to be equal to MAN. And what are those forces? Well, it looks like W cosine theta minus F, because F is pointing in the opposite direction of N, that's equal to MAN. And if we plug some numbers in, then we get 15. This is 0. 15 cosine theta. That's equal to 15 over G. This is W over G, 15 over 32.2. Okay, that's going to be times, it's in bed is what? It's V squared over rho. Okay, so this is V squared over rho is 3. So what is this? This is, these cancel. We get cosine theta equals V squared over, this is 96.6. Okay, and we want the angle, and so we need to resolve V squared, which is where we can use this idea of the conservation of energy. So in order to do that, we're going to have to calculate the change in the potential energy of the due to gravity, right? So if this is L, then, and this is theta, then this is L cosine theta, right? And this distance here is L minus L cosine theta, right? So L times 1 minus cosine theta. Okay, and so if we use the equation T plus V equals T plus V, then we get T naught plus V naught equals T1 plus V1, right? And I guess we can add that to our list over here. T naught plus V naught equals T1 plus V1, all right? And we have T naught is what T naught is when we're up here. It's the kinetic energy system was released from rest, right? Okay, so V naught, well, it hasn't, if we use this as a starting point and define down as moving in a positive direction for the relative to the weight, then 0. Okay, so 0 plus 0 equals 1/2 mv squared. Hey, look at that, mv plus we got w times the distance, right? So this is y, and y is negative, so this is a negative sign, times L 1 minus cosine theta. Okay, so plugging numbers in, we get, let me move things over here. I guess I don't need to. 1/2 m is 15 over 32.2 v squared. Say equals, because cans is 15 times 3 times 1 minus cosine theta. Okay, so the 15's cancel. 2 times 32.2 times 3. So v squared equals this times this times this is 193.2. So we just did it. 1 minus cosine theta. Okay, so I have something to plug in here. Okay, well, let's move this out to the main room, and we'll say cosine theta equals, and then 193.2 over 96.6 is 2. 1 minus cosine theta. Okay, so cosine theta equals 2 minus 2 cosine theta. So there's 3 cosine thetas. So let's say 3 cosine theta is 2. And so what does that mean? It's theta is the inverse cosine of 2/3. And that is 48.189 degrees. So what's basically happening is that there's a weight, and when it gets just beyond halfway, so 45, just beyond halfway, it's the centrifugal force of that the ball is experiencing is trying to sort of push it out, and at a little past 48 degrees, that's the balance point. So now you know, and I will see you in the next video.